the gradients in quasi-Fermi level. Quasi-Fermi level എന്താണെന്നുള്ളത് നമുക്ക് already അറിയാം. നമ്മൾ യൂസ് ചെയ്യുന്ന സെമികണ്ടക്ടറിലെ കാരിയർ കോൺസെൻട്രേഷൻ എന്ന് പറയുന്നത് എക്സസ് കാരിയേഴ്സ് ആണെങ്കിൽ, അതായത് അഡീഷണൽ ആയിട്ട് എക്സസ് ആയിട്ട് നമുക്ക് കാരിയേഴ്സ് ആഡ് ചെയ്തിട്ടുണ്ടെങ്കിൽ, in order to represent the excess carrier energy level, we are using quasi-Fermi levels instead of Fermi levels, which represents the number of or probability of finding majority carrier concentration. In addition to Fermi level, we are using quasi-Fermi level only to represent excess carrier concentrations. So, excess carrier concentration represent ചെയ്യുന്ന quasi-Fermi levels ആണ് ഏതെങ്കിലും തരത്തിൽ ഗ്രേഡിയന്റ് അഥവാ വേരിയേഷൻസ് ഒരു ഡിഫറൻസ് ഉണ്ടാവുകയാണെങ്കിൽ അത് എങ്ങനെയാണ്, അത് ഏത് രീതിയിലാണെന്നൊക്കെ അനലൈസ് ചെയ്യാൻ വേണ്ടിയിട്ടാണ് ഈ ഒരു ടോപ്പിക്ക് പഠിക്കുന്നത്. നമുക്ക് നോക്കാം. Quasi-Fermi levels are used to express total hole or electron concentration when excess carrier concentrations are exist. At equilibrium condition, നമുക്ക് equilibrium condition നോക്കുകയാണെങ്കിൽ നമ്മൾക്ക് അവിടെ ഇലക്ട്രോൺസിൻ്റെ അല്ലെങ്കിൽ ഹോൾസിൻ്റെ ഫർദർ ആയിട്ടുള്ള മൂവ്മെൻറ്റ്സ് ഒന്നും ഉണ്ടാവുന്നില്ല. ഇൻ സച്ച് കേസ് അവിടെയുള്ള ഗ്രേഡിയൻറ്റ് അഥവാ ഡിഫറൻസ് ഇൻ ഫെർമി ലെവൽ എന്ന് പറയുന്നത് 0 ആണ്. ദർ വോണ്ട് ബി എനി ചേഞ്ച് ഇൻ ദ കേസ് ഓഫ് ആ ഫെർമി ലെവൽ. EF എന്ന് പറയുന്നത് എനർജി ലെവലിൽ വേരിയേഷൻ ഒന്നും ഉണ്ടാവില്ല. ബട്ട് അവിടെ ഒരു സെമി കണ്ടക്ടറിലുള്ള ടോട്ടൽ കറണ്ട് പ്രൊവൈഡ് ചെയ്യുന്നുള്ള ഡ്രിഫ്റ്റ് അല്ലെങ്കിൽ ഡിഫ്യൂഷൻ കറണ്ട്സിൽ ഏതെങ്കിലും തരത്തിൽ വേരിയേഷൻ ഉണ്ടെങ്കിൽ ഇക്വിലിബ്രിയം കണ്ടീഷനിൽ നിന്ന് മാറിയിട്ട് അത് സ്റ്റഡി സ്റ്റേറ്റ് കണ്ടീഷൻ ആവും. ഇൻ ദാറ്റ് കേസ് ദർ വിൽ ബി സം ഗ്രേഡിയന്റ് ഇൻ ദി condition of that semiconductor. At the equilibrium condition, there is no gradient in the Fermi level, but in steady state condition, there is some gradient due to drift and diffusion current. If there is any difference in drift or in diffusion, it shows some gradient in the quasi-Fermi levels. So, the non-equilibrium electron current density due to drift and diffusion is given by, if I am taking an n-type semiconductor, then current density in that semiconductor Jn of x equal to Jn drift plus Jn diffusion. And I have to write the equation for Jn drift, that is current density due to drift and current density due to diffusion here, which we discussed in the previous classes. And the equation will be Q mu n n of x E of x plus Q dn of x by dx. Right? Mu n represents the mobility of electron and dn is the diffusion constant. Then we already know the equation for n of x equal to ni into e raised to fn minus ei by kT, where ei is the intrinsic energy level and fn is the quasi-Fermi level of electron. Excess carrier electron in the energy level and quasi-Fermi level and fn എന്ന് പറഞ്ഞിട്ട് represent ചെയ്യാറ്. So, the gradient in electron concentration is represented by the rate of change, or d by dx of n of x. We already know the value of n of x and we have to differentiate with respect to x. d by dx of ni into e raised to fn minus ei by kt. Here fn and ei means it actually the function of x or the position or that area. So after differentiating this, we will get ni into e raised to fn minus ei by kt into 1 by kt, and this e raised to fn minus ei you have to consider separately, that is dfn by dx minus dai by dx. Then after simplifying this equation, we know ni into e raised to fn minus ei by kt means n of x. In this we wrote this equation and I wrote that term as n of x in divided by kt into dfn by dx minus dei by dx, and this is equation number 2. Then substituting equation number 2 in equation 1, instead of dn of x by dx in this diffusion current term, we are substituting this equation number 2. Then the equation will be Jn of x equal to q mu n n of x e of x plus q dn n of x by kt dfn by dx minus de by dx. Then we already discussed the Einstein relation. Instead of this q, dn and kt, we have to substitute the mobility term. So dn by mu1 equal to kt by q. This is from Einstein relation, and from this equation we are finding an equation for mobility of electron, mu(n) equal to dnq by kt, that is which is given in this term. Then by substituting that value, we will get q mu n n of x e of x plus mu n n of x into dfn by dx minus dei by dx. Then from the Einstein relation itself, we know dei by dx equal to q into e of x or epsilon x from Einstein relation, and substituting the value here, instead of dei by dx, we will get Jn of x equal to same term, and instead of dei by dx we are substituting q into e of x. Then removing the opening the bracket, we'll get q mu n n of x into e of x plus mu n n of x into dfn by dx minus mu n n of x into q into e of x. Then here these two terms, first term and third term, are similar. Cancelling that term, on it we get the equation of total current density Jn of x equal to mu n n of x into dfn by dx. And multiplying this this RHS of this equation and multiplying and dividing by q, will get, multiplying numerator and denominator of RHS by q, will get Jn equal to q mu n n of x into dfn by q dx. Then the equation will be q mu n n of x into d by dx of fn by q. This actually we are rearranging this above equation of current density, that is Jn equal to q mu n n of x into d of fn by q by dx. Since we know the equation of conductivity sigma equal to q into mu n into n of x, that is conductivity, sigma equal to conductivity, and we already discussed this equation in the class of drift current due to drift current in the semiconductor. Substituting this conductivity term in this above equation of current density, therefore Jn equal to sigma n of x d sigma n of x dfn by q by dx. That is this is the current density equation of an n-type semiconductor, and for a p-type semiconductor, instead of n you have to write p, that is Jp equal to sigma p of x, that is conductivity of holes, into d by dx of fp by q. That is, from here you can say fn by q means the gradient in the Fermi level, quasi Fermi level, due to the excess carrier. Q means the charge and Fn is the energy level, and the variation in the Fermi level due to charge. That is actually represented by this term, the second term, that is total current density due to electrons and hole is equal to the derivative of quasi Fermi level, that is derivative of quasi Fermi level, where sigma is actually the constant value. This is the gradient in quasi Fermi level.